Particulate matter 2.5 is not a specific chemical compound. It is a strictly physical classification for any suspended solid or liquid droplet with an aerodynamic diameter of 2.5 micrometers or smaller. This exact dimensional threshold governs how the mass interacts with the human body. Larger dust particles are trapped by the mucous membranes and cilia of the upper respiratory tract. A 2.5 micron particle is small enough to completely bypass these anatomical defenses. Instead, they travel deep into the alveolar regions of the lungs. From there, they cross the pulmonary epithelium directly into the systemic circulatory system. Once inside the bloodstream, these fine particles trigger a cascade of extrapulmonary damage. They introduce free radicals that cause oxidative stress, provoke systemic inflammation, and disrupt the autonomic nervous system, leading to cardiac arrhythmias. Because the toxicity of this pollutant is dictated by its aerodynamic profile rather than its chemical makeup, engineering a tracking system requires measuring an invisible physical dimension. Historically, environmental protection agencies focused on visible pollution. They regulated heavy, coarse industrial dust and opaque smoke plumes. That approach shifted following the 1993 Harvard Six Cities study. Researchers tracked over 8,000 adults and determined that life expectancy was dictated by invisible fine particulate concentrations, not overall visible dust. Residents in cities with the highest fine particulate loads faced a 26% higher risk of mortality. This data forced the United States Environmental Protection Agency to establish the first national ambient air quality standards specifically targeting PM2.5. As epidemiological evidence has grown, regulators have continuously tightened these limits. In 2024, the EPA lowered the primary annual standard to a strict 9.0 micrograms per cubic meter. Enforcing a threshold this localized and stringent reveals an architectural problem. Traditional regulatory hardware, like this bulky Federal Reference Method monitor, costs tens of thousands of dollars. They are highly accurate, but too expensive to deploy densely across a single city. To provide the hyperlocal data required by these new standards, monitoring networks now supplement high-precision reference monitors with dense, geographically overlapping grids of low-cost optical sensors. The internal architecture of these low-cost devices relies on precisely directed airflow. A microfan draws ambient air into the sensor housing through a geometric inlet. This inlet pathway structurally filters out larger debris and forces the airstream into a stable, laminar flow, channeling the remaining fine particles directly across a focused laser beam. When particles intersect this laser, they cause the light to scatter in multiple directions. A photodiode positioned perpendicularly to the beam captures these scattered light flashes. The sensor's internal microprocessor applies Mie-scattering theory to classify these optical pulses. It groups the incoming flashes into specific size bins based on their intensity and duration. To convert those binned light flashes into a final mass concentration, the algorithmic logic makes a physical assumption. It assumes every captured particle is a perfect sphere, possessing identical standard density. These devices do not physically weigh anything. The entire modern PM2.5 tracking ecosystem relies on an optical proxy, measuring scattered light and applying rigid geometric formulas to estimate a mass it never actually touches. Running a laser diode and microfan continuously at the edge of a network causes rapid mechanical degradation. To extend the hardware's lifespan, engineers program strict duty cycles via UART communication protocols. The firmware systematically pulls the sensor's pins low to put the device to sleep, then periodically wakes it to sample the air. Waking the unit introduces a physical lag. The internal fan requires a strict 30-second delay state to clear out stagnant dust and physically stabilize the laminar airflow. If the primary microcontroller queries the data payload before this stabilization period completes, the sensor returns errors that will permanently corrupt a time series database. Operating reliable environmental edge networks requires disciplined state management, ensuring the physical mechanics are fully stabilized before any data is recorded. At a physical level, the sensor cannot distinguish between solid aerosols and water vapor. Humidity scatters laser light in a pattern nearly identical to solid particles. When ambient relative humidity climbs above 80%, optical sensors record a massive positive bias. They interpret water droplets as solid mass, wildly overestimating actual pollution levels. While raw sensor data tracks general trends, it lacks the precision required for legal compliance. Closing that gap requires aggressive statistical correction in the cloud, utilizing multiple linear regression models. Data scientists feed secondary environmental features, such as ambient temperature, humidity, and co-located nitrogen dioxide levels into random forest algorithms. These models mathematically isolate the water vapor signature and subtract it, significantly reducing the root mean square error. This line graph charts raw PM2.5 estimations against actual calibrated mass. The overlaying curve demonstrates the United States EPA's proprietary polynomial correction formula, specifically designed to drive down the humidity bias in optical networks. The equation operates as a piecewise function. At standard concentration ranges, it applies a scaling factor and subtracts the humidity interference. However, if the sensor detects extreme concentrations, like dense wildfire smoke exceeding 300 micrograms, the logic dynamically shifts to a quadratic fit to maintain accuracy. The system builds accuracy by using cloud-based statistical models to systematically erase environmental noise in real time. Processing this calibrated data introduces a data ingestion challenge. Systems must simultaneously handle high-frequency, multivariate payloads from tens of thousands of decentralized nodes globally. Organizations deploy fault-tolerant extract, transform, load pipelines. Data engineers use these architectures to pull disparate JSON structures from various sensor manufacturers and normalize them into a single interoperable schema. Before this data is committed to the primary warehouse, unsupervised anomaly detection algorithms, like isolation forests, scan the incoming stream. They identify and strip out hyperlocal outliers, ensuring that a sudden spike from indoor cooking does not corrupt the broader neighborhood average. A single low-cost optical sensor is inherently noisy, but a dense geographically overlapping network, properly filtered through a rigid cloud data pipeline, achieves an algorithmic resilience capable of outperforming isolated reference monitors. Despite their statistical accuracy, optical networks possess a rigid limitation. They cannot perform chemical speciation. To an optical laser, highly toxic heavy metals emitted from an industrial refinery look geometrically identical to benign sea salt blowing off a coastline. While engineers have perfected the spatial tracking of mass, scientific and regulatory consensus is rapidly pivoting toward a more elusive threat, ultrafine particles, or PM2.5. This chart compares total particle mass against particle count. Ultrafine particles represent a tiny fraction of overall mass, yet constitute the vast majority of physical objects in urban air. Therefore, lowering PM2.5 mass doesn't necessarily reduce the sheer particle number generated by modern combustion engines. Smaller than 0.1 micrometers, these particles carry unprecedented toxicological risks. Upon inhalation, they bypass cellular defenses and cross directly over the blood-brain barrier. Optical sensor networks have successfully democratized our ability to map atmospheric mass. The next critical public health challenge is solving the engineering reality of real-time nanoscale chemical speciation.